Welcome back. We begin a series of lectures on the joy of calculus. You know, just the other day I saw my dentist, and my dentist actually told me that my mouth was full of calculus. I got very excited. The dentist didn't think it was such great news, but for me, for a mathematician, to have a mouthful of calculus, well, I was thrilled. Actually, the words calculus, calcium, calculate, they all have the same root, which is calculus, which literally means pebble. And pebbles were the first calculating devices. So, right, we learned to count 1, 2, 3 at a time using pebbles. In calculus, we learn to calculate how things grow and change. There are many applications to this, from the motions of the planets. Physicists study the interaction of particles. Chemists study how substances and physical objects, how they change, how they interact. All of these things involve motion and change. We're also going to learn in this course how to perform at optimal efficiency using some simple ideas from calculus. In fact, in the next 3 lectures, I hope to convince you that calculus is not only important, but can also be a lot of fun. For instance, in this lecture, we'll have fun with functions. Hey, you can't even say the word functions without saying the word fun. But seriously, we'll learn how they grow and how they change over time. In the next lecture, we'll take advantage of this knowledge to arrive at a phenomenal way to approximate any function with a polynomial. That's pretty important because there are all kinds of functions out there in the world, and the polynomials are the simplest of functions. So in a way, we're going to take anything, no matter how complicated it is, and be able to approximate it with something much simpler. In our 3rd and final lecture, we'll explore the fundamental theorem of calculus. Again, you can't say fundamental theorem of calculus without the word fun, and how it allows you to calculate areas and volumes that were impossible to calculate when we only had the tools of geometry and trigonometry at our disposal. So we begin with calculus with the study of slopes. Now, before you say, oh boy, why should I care about slopes? The fact of the matter is, every day we encounter slopes. Anytime we're talking about how one quantity varies with another quantity, we're dealing with a slope. So if you're talking about, miles per gallon, or feet per second, or miles per hour, or how much price you're paying per pound, all of those ideas are talking about how one quantity varies with another, and so you are talking about slopes. Now, mathematically, the simplest objects to be focusing on are the straight lines, right? The lines where the slope is constant throughout the line. For instance, let's take a look at this function, y equals 2x plus 3. Okay? We know from our earlier discussion on algebra that this line has a slope of 2. That means if x increases by a little bit, then y will increase by twice that little bit. In fact, if you take that line and you move it straight up or straight down, like let's say you get y equals 2x minus 5, then that line also has the same slope. That parallel line also has a slope of 2. Here's another line. Let's say y equals 4x minus 1. That's a much steeper slope, right? You wouldn't want to be walking up that hill. That has a slope of 4. Whereas the line y equals negative x, that has a constant slope of negative 1. That's a sliding board. You wouldn't mind going down that as a sliding board. And then finally, a constant function, which is also a straight line, like y equals 5, that has a slope of 0. Okay, and that's actually going to be a very important line to be thinking about for later. That is the straight line, the horizontal line, that has a constant slope of 0. Okay. So now, lines are fine. Lines are simple, right? You have the same slope everywhere. But calculus is all about taking advantage of what we know about lines and applying them to curves, things that are not nearly as simple. Like, for instance, let's take a look at this parabola, y equals x squared plus 1. Now, if I asked you what's the slope of that parabola, you'd say, well, you're crazy, right? That the slope is constantly changing, right? When you're on the left side of the graph, that parabola is decreasing. The function is decreasing, right? So the slope is negative. When you're on the right side of that parabola, the function is increasing, right? When x is bigger than 0, it's increasing, so your slope is positive. Right there at the bottom of that parabola, the slope is 0. So to ask what's the slope of that parabola, well, that doesn't make any sense. But now I ask you at a specific point, okay? Let's say when x is 3, okay? When x is 3, first of all, what's y? Y is going to be equal to 3 squared plus 1, which is 10. So let's look at that point, 3, 10, on the parabola. And I ask, I want to ask how fast is that function growing at the point 3, 10? Well, now I don't have a line in front of me, but the line that I'm interested in looking at is I want to look at the slope of the line that just touches the graph at that point 3, 10. Okay? That line is called the tangent line. And our mission for the next few minutes is to calculate the slope of that tangent line. Now, I've got some good news and some bad news. The bad news is in order to calculate the slope of a line, those slopes of lines are easy to calculate, but you need 2 points to figure out the slope, right? But the good news is we can get pretty close. We can get close to figuring out that even though we only have the point 310 at our disposal, we'll take another point that's close to 310 that also lies on the parabola. So using 310 and another point, let's call that point, instead of x being 3, let's look at x being equal to 3 plus h, where h means it's just a hair's length away from 3. Okay, so at the point where x is equal to 3 plus h, and the y value for that, well, what would the y value for that be? I'd have to square it. I'd have to take 3 plus h squared and add 1 to it. And when you expand that, you get h squared plus 6h plus 10. Okay, so now I have 2 points on the parabola. The first point, which I'll call x1, y1, is equal to 310. The second point, which I'll call x2, y2, is equal to 3 plus h followed by h squared plus 6h plus 10. Now, to calculate the slope of the line that goes through those 2 points, we have to calculate, as we've done before, the change in y divided by the change in x. And the symbol that they use in calculus to express that is they use the delta symbol, the triangle, the Greek letter delta, to represent the word change in. Okay, so to calculate the change in y divided by the change in x, we look at delta y over delta x. Algebraically, that's equal to y2 minus y1 over x2 minus x1. Now we have y2 and y1 and x2 and x1 in front of us. H squared plus 6h plus 10 minus 10, that's the change in y. 3 plus h minus 3, that's the change in x. When you simplify that, that's h squared plus 6h divided by h. And when you divide through by h, you're left with h plus 6. Now what does that tell us? That says that the slope of the line that goes through the point 310 and the point very close to 310 is equal to h plus 6. Now, as we let h get closer and closer to 0, the slope of that line gets closer and closer to 6, right? When h is 0, that 6 plus h becomes 6. So as h gets really, really close to 0, we have effectively a slope of 6. And therefore, the slope of the tangent line is 6 when x is equal to 3. We could go through the same argument for other points on the parabola, not just the point where x equals 3. And if you go through that same algebra, let's say at the arbitrary point x squared plus 1, then the slope that you get when you do the algebra is simply 2x. Okay, so if you can calculate 2x, then you can calculate the slope. For instance, when x is equal to 1, the slope of the tangent line is simply 2. When x is equal to negative 3, then the slope of the tangent line is twice negative 3 is negative 6. At x equals 0, like we noticed before, the slope of the tangent line is 0. So, in general, if I have the function y equals x squared plus 1, then the slope at the point x is equal to 2x. And we represent that with the notation y prime is equal to 2x. Y prime, we call that the slope function or the first derivative. I want to say one other thing about this function. If I take that function y equals x squared plus 1 and I raise it higher or bring it lower, that tangent line still has the same slope as it did before. So if I was looking at the function x squared plus 17, then we would still have y prime is equal to 2x. Or if I'm looking at y equals x squared plus 0, which I'll talk about later, y equals x squared, then that has a derivative of 2x. The official definition of the derivative, and I'll just say it here once, for any function y equals f of x, we define the derivative to be y prime as f of x plus h minus f of x divided by h. That's the change in y divided by the change in x. And we take the limit of that as h goes to 0. So just let h get really, really, really small and look at what that fraction is going to. And that's your derivative. Calculating this is called differentiation. And I'll mention there's some other notation for this. Aside from using y prime, mathematicians will also use the expression f prime of x. You'll see me use that later on. And dy dx. So we just calculated that if y is equal to x squared, that its derivative y prime is equal to 2x. Now I've got good news for you. We don't have to go through that long, laborious process to calculate the derivative every time we need one. By doing the same kind of arguments, we can come up with some general rules for calculating derivatives. For example, if y is equal to x cubed, then the derivative is 3x squared. Y prime is 3x squared. If y is equal to x to the fourth, then its derivative, y prime, is equal to 4x cubed. Can you figure out the next one? If y were equal to x to the fifth, what would y prime be? It would be 5x to the fourth. Exactly. If y is equal to x to the nth power, then what should the derivative be according to our pattern? It would be n times x to the n minus first power. This is known as the power rule. By the way, even when the exponent is 1, right, y equals x, what would the derivative of that be? That would be 1 times x to the 0 power, but that's just equal to 1. 1x to the 0 power is 1, and that makes sense because the slope of the line y equals x is constantly 1. Here are some other easy rules for differentiation. Multiplying by a constant. You can multiply by a constant with abandon. For instance, since y equals x squared has derivative 2x, then y equals 10x squared, what would you want the derivative to be? It would be 10 times 2x, and you'd be right. It would be 20x. Okay, so multiplying by a constant is simple. The other simple rule is the derivative of the sum is equal to the sum of the derivatives. Okay, so for instance, if you knew that the derivative of 4x cubed was 12x squared, and the derivative of 8x squared is equal to 16x, and the derivative of negative 3x, that's equal to negative 3, and the derivative of 7, now that's a constant function, y equals 7, that has a derivative of 0, then if you want the derivative of the sum of all those functions, 4x cubed plus 8x squared minus 3x plus 7, then we have the derivative of the sum is the sum of the derivatives. We would get 12x squared plus 16x minus 3. Okay, now you know how to calculate some derivatives. What can you do with it? Let's take a look at this function. Y equals x squared minus 8x plus 10. Okay, I've got a graph of this function here. And here's a more interesting question. Where is that function minimized? Where does that function reach its low point? Okay? Now remember what we said about slopes, about derivatives. When a function reaches its low point, what is the slope of the tangent line? It's 0. That's a very simple but powerful idea. Wherever a function reaches its minimum or its maximum, that is, whenever we go from decreasing to increasing, or whenever we go from increasing to decreasing, the slope of the tangent line is 0. So if we were interested in this function, x squared minus 8x plus 10, and we wanted to know where is that function minimized, then how do you find it? Easy. We take the derivative, we find out where is the derivative of that function equal to 0. Can you differentiate x squared? Sure, it's 2x. Can you differentiate minus 8x? Sure, it's minus 8. And can you differentiate 10 with respect to x? Yeah, that's 0. So the derivative of x squared minus 8x plus 10 is 2x minus 8. When does that equal 0? Well, we solve 2x minus 8 equals 0, and we get x equals 4. So that function is minimized when x equals 4. Let's do an application of this where you might actually care about solving a problem of this sort. Let's look at Laurel's lemonade. Laurel, my daughter, by the way, had her first lemonade stand a couple years ago, and she got very nervous. We put out this big sign and said Laurel's lemonade on it, and she said, "Oh, Daddy, no one's going to buy my lemonade because they're going to think that the lemonade's all for me because it says Laurel's lemonade." I assured her that, no, people know what that sign means. And then we had to decide on the price of the lemonade. How much should she be charging per cup? So we did some statistical analysis, and we decided that if she charged X cents per cup, then we thought she would sell 50 minus X cups that day. The idea being that the bigger the price, the fewer cups she would sell. Okay? And so now the question at hand is, let's find the value of X that will maximize Laurel's revenue. And she doesn't have any costs, by the way, because her parents bought the lemonade for her. Okay, so she gets to keep all the money. So what's her revenue going to be? It's going to be, she's going to get X cents for every one of the cups that she sells. So if she sells 50 minus X cups, then her revenue is X times 50 minus X, which is 50X minus X squared. That's our revenue function. If she charges a price of X, then she's going to make 50X minus X squared cents. Let's call that function R of X. Now, if you look at that function R of X, you have an upside down, you have a parabola. It's an inverted parabola maybe, right? And where is that function maximized? She's interested in maximizing her money. So we set the derivative of 50x minus x squared equal to 0. So the derivative of 50x minus x squared is 50 minus 2x. Where does that equal 0? When x equals 25. So if she charges x equals 25 cents, then she expects to earn 25 times 50 minus 25. That is 625 cents, or $6.25. My favorite calculus problems when I was first learning calculus were of the next variety. Let's get Laurel's sister into the act, Ariel. Let's say Ariel wants to create a box for Laurel so she could keep her cash and her supplies in. And she's going to make that box, without a lid, by the way, from a 12-inch piece of cardboard. And so to create the box, she's going to cut 4 squares out of the corners of that cardboard, and she's going to fold up the edges, okay, just like in our picture. All right, so if she cuts out an x by x square out of each of the corners, the question is, what will the volume of the box be? Well, the volume of a box is going to be the length times the width times the height. If she cuts out an x by x square from each of the corners, then the length of each side is going to be 12 minus 2x. So the length will be 12 minus 2x, the width will be 12 minus 2x, and the height that we get from folding the tabs up is x. So the volume is 12 minus 2x times 12 minus 2x times x, which if you expand that, you get 4x cubed minus 48x squared plus 144x. Okay, so what we want to do is maximize that volume. So how do we do it? We take the derivative of the volume and set it equal to 0. Now, can you do the derivative of v of x, v prime of x? Well, by the power rule, the derivative of 4x cubed is 12x squared, minus the derivative of 48x squared, that's minus 96x, plus the derivative of 144x, that's 144. Set that equal to 0. I notice that all the numbers there are divisible by 12, so let me divide everything through by 12. That simplifies things. It's x squared minus 8x plus 12 equals 0. We can factor that polynomial, here's an actual application of factoring, to get x minus 6 times x minus 2 equals 0. Now, if the product of two numbers is 0, how can that happen? Only if one of those numbers is itself 0. So that means either x minus 6 is 0 or x minus 2 is 0. That means that your answer will either be when x equals 6 or when x is equal to 2. And you could tell either by looking at the graph of that function or by actually plugging in the numbers that when we let x equal 6, then the volume of the box is 0 because we've cut the whole box off, right? It was a 12-inch square box. If we were cutting off 6-inch squares, we've obliterated the box entirely, right? Similarly, if x had been equal to 0, we wouldn't have done any folding of the box. We would have seen a volume of 0. But when x is equal to 2, then we get our biggest volume. That's going to be a volume of 12 minus 2x times 12 minus 2x times x. That's 12 minus 4 times 12 minus 4 times 2. That's 128 cubic inches. Now, the more derivatives we know, the more problems we can solve. So far, we've only been solving problems involving polynomials. But the power rule actually is even more powerful than it sounds. The derivative of x to the n is nx to the n minus 1. It turns out that rule works for any exponent n. That exponent could be doesn't just have to be a positive integer. It could be a negative integer or a fraction. It'll still work. So for instance, y equals x to the negative 1 power, okay? That's the function y equals 1 over x. The derivative of that, by the power rule, would be negative 1 times x to the negative 1 minus 1. That's the negative 2 power. In other words, y prime would be negative 1 over x squared. If we were interested in differentiating y equals 1 over x squared, right, that would be y equals x to the negative 2 power. If you differentiate that, you get negative 2 x to the negative 3 power, or negative 2 over x cubed. Or here's a derivative we'll see later, y equals the square root of x, right? That's y equals x to the 1/2 power. Well, if you differentiate that, we get 1/2 x to the half minus 1. That's 1/2 x to the negative half power. That's 1 divided by 2 square roots of x. So the power rule is really a very powerful rule. Here are some other functions that you might be interested in differentiating. For instance, the trigonometric functions and the exponential functions. Whenever we talk about things like, oh, how sound waves travel, or how your money grows, or how the population grows, those are things that are modeled by trigonometric functions and by exponential functions. And these are rules that are well worth memorizing. The derivative of the sine function is the cosine function. That is, if y equals sine of x, then y prime equals cosine of x. The derivative of the cosine function, on the other hand, is the negative of the sine function. That is, if y equals cosine x, then y prime equals negative sine x. The most important function in calculus is the function y equals e to the x, because the derivative of e to the x is itself e to the x. The function not only tells you, when you plug in x, not only do you get a value of y, you also get the slope of the tangent line, how fast that function is changing. And the derivative of the log of x is equal to 1 over x. Those are all very useful functions to know. Let me try and give you some motivation for one of those rules. Why should the derivative of sine x be equal to cosine x? Okay? So now, well, let's take a look at the graph of the sine function just to see how it's increasing and decreasing. Okay? So here we have the graph of y equals sine x. And let's calculate or estimate the slope at various points along the graph. For instance, when x is equal to 0, the slope of that sine function looks pretty much like 1. Right? It looks like it's growing like the line y equals x. So we'll put a slope of 1 at the point 0. How about at the point x equals pi over 2 at 90 degrees? When it's at its high point, then we have a slope of 0. Okay, so let's mark that point as having a slope of 0. Back when we're down at pi at 180 degrees, then we have a slope of negative 1, right? That line, that tangent line looks a lot like the line y equals negative x shifted over. At the bottom of the graph, at 3 pi over 2, we again have a slope of 0. At x equals 2 pi, we're sort of back to where we started. We again have a slope of 1. And so we're going to have these slopes of 1, 0, negative 1, 0, 1, and that pattern is going to get repeated forever. Now, if we connect the dots along those, if we connect the dots of our slope function, then we see it looks an awful lot like the cosine function. Incidentally, if I replace all the points of that cosine function with pigs, yes, pigs, then we get a special function in mathematics called the coswine function. But I won't say any more about that. That's a subject for advanced trigonometry. By the way, you'll notice at the bottom of those functions, at the troughs of the function, is where those pigs are feeding. Here's another differentiation rule. I mean, we know that the derivative of the sum is the sum of the derivatives. What about the derivative of the product? Is that the product of the derivatives? It would be nice, but alas, it would not be true. Let me quickly give you the product rule. If y is equal to f of x times g of x, then y prime is equal to, here's how I remember it, the first times derivative of the second plus derivative of the first times the second. That's f of x g prime of x plus f prime of x g of x. For example, if we're looking at y equals x squared times the sine of x, we know the derivative of each of them. We can use that to find the derivative of its product. So the derivative of the product is first times derivative of the second. That would be x squared times cosine x plus derivative of the first times the second. The derivative of x squared is 2x times sine x. So when you add those together, you get its derivative. If we can do products, we can also do quotients. Here's the quotient rule. It says if y equals f of x over g of x, then y prime is equal to g of x times f prime of x minus f of x times g prime of x all over g of x squared. Now, yuck, that's a mouthful. How do you remember that? Here's how I remembered that in high school. Let's say, instead of writing it as f of x over g of x, think of it as high over low. Or, to make it sound even funnier, high over ho. Okay, then y prime can be remembered as ho d high minus high d ho over ho ho. Okay, so that's a funnier yet accurate differentiation rule. For instance, let's suppose you wanted to calculate the derivative of the tangent of x. That's sine of x over cosine of x. Now, before I give you the derivative, let's say why might you want to calculate the derivative of the tangent of x. Let's say I had a yo-yo here on a string, and I wanted to calculate, let's say I was moving this yo-yo at a constant speed, okay, then this might be an elementary model of planetary motion here, then what the tangent of x is telling you is the slope of the rope or the slope of the string when you are at time x. And what the derivative of tangent of x is telling you is how fast is that slope changing at the time x. Okay, so how would we calculate that by the Heidi-Ho law? Well, we take bottom times derivative of the top, that's Hodi-Hi is cosine x times cosine x, minus top times derivative of the bottom, Heidi-Ho, that's minus sine x times negative sine x, all over ho-ho, cosine x squared. But the numerator winds up being cosine squared plus sine squared, which equals 1. So the derivative of the tangent function is 1 over the cosine squared of x. So as we said at the outset, calculus is the mathematics of how things grow. And in general, there are three ways that we see functions growing. They either have a constant growth, and those functions are represented by straight lines. You see functions that grow proportional to their input. For example, a falling body is traveling faster and faster according to how long it's been traveling. That's, for instance, why when you look at water shooting out of a fountain, that the curves that you see are parabolas. Finally, you see functions growing that are proportional to their output. That's things like how your bank account grows or how the population grows. All of these are described by things called differential equations. And sometimes these things involve taking derivatives of derivatives. Those are called second-order differential equations. Mathematics, being the language of science, is actually expressed. The laws of nature are expressed through differential equations. For instance, we see examples that arise in epidemiology. They can describe pendulum motion, vibrations, pacemakers, even the beating of your heart. In fact, it's safe to say that on some level, your life actually depends on calculus.